So we're going to take our first step into a larger world. And what I mean by that is we're going to discuss the factorial ANOVA, which is still a univariate statistic. Univariate meaning single variable, but that's referring to the outcome. We still have a single DV. What factorial ANOVA allows us to do is start adding additional independent variables. So we're basically going to be talking about an introduction to the factorial ANOVA, what it's capable of doing, and then we're going to stick with the most simplest of designs that we can with the factorial ANOVA, computing a two-factor ANOVA. So basically looking at two separate independent variables, each with two levels. So if you think about that, that basically means that we have independent variable 1, which has two levels, and independent variable 2, which has two levels. And when you start to think about it, even that is fairly complex because we now have multiple possible combinations. 1 and 1, 1 and 2, 2 and 2, 2 and 1. So again, we've increased the number of possible interactions that are going on. Not only that, we're looking at basically examining first the omnibus test. Is there a difference in general? Then we're looking for what's called main effects. And those main effects are is there a significant difference within each independent variable? And then we're looking for the simple main effects. And this is an unfortunate title, but just make sure that you get it clear that a main effect is looking at a single independent variable. A simple main effect is looking for the interaction between the two variables. And we'll be getting into this in more detail, and hopefully it'll become clearer. And again, we'll be discussing briefly that you can use a factorial ANOVA for much more complex designs. But as we add complexity to the designs, we're also obviously adding complexity to the understanding and the process of analysis. So the whole goal here is to add one more thing to our statistical toolkit, the factorial ANOVA, at least in its simplest form. So again, let's start with the assumptions. The assumptions of the ANOVA are that we have a categorical IV or IVs at this point, because we're now talking about not a simple ANOVA, or we're talking about a factorial ANOVA. And factorial just means that we're looking for multiple factors. That's often what ANOVA will call a categorical IV. Each categorical IV is often referred to as a factor. So our first independent variable is factor 1, second independent variable, factor 2. We still have a continuous, normally distributed DV, and that's a single variable. We have one outcome. Now, we also need to look at homogeneity of variance, and again, we're back to the Levene's test that we first saw with the t-test, and that's because we want to make sure that there is a normal distribution in each and every one of our factor conditions. And again, if it's a 2x2 design, that means there's a total of 4 factors. There's 4 categories that someone could be in based on the independent variables. Again, we want to see this insignificant. We're looking for, this is the only time that we actually want to see that significance above 0.05. Because if it is significant, 0.05 or lower, it means that there is a significant, meaningful difference, not just in the means or the averages, but also in how those distributions look. And that is a problem that we need to adjust for. So single factor designs within and between have only one independent variable. Factorial designs have more than one independent variable. Test effects for each independent variable or factor, and test effects for the unique combinations of each level of each factor on each other. Other specifications, each factor can have 2 or more groups or levels, and the number of levels for one factor does not have to be the same as the level of groups for the other factor. So we're primarily going to focus on what's called a 2x2 factorial ANOVA. That means that there are 2 factors or 2 independent variables. Each one has 2 levels. But we could easily be looking at a 2x3 factorial ANOVA. So we have 2 variables, one with 2 levels and one with 3. We could look at a 3x3 factorial ANOVA. That's 2 variables, 2 factors, each with 3 levels. And we could even look at more complexity, such as a 2x2x2 design. So that would be an example of 3 independent variables, each with 2. But again, there's no restrictions. We could be looking at a 2x3x4 design. 3 factors, one with 2 levels, one with 3 levels, and one with 4 levels. The complexity continues to go up. We could have as many independent variables with as many levels as we want, as long as each one is categorical. That's really the only requirement. Now, as I said, it starts to get ridiculously complex in how we analyze that information, which is why we're going to stick with the 2 by 2 for this class. So the two-factor ANOVA, previously we compared one null hypothesis to one alternative hypothesis. A two-factor ANOVA test has three hypotheses, each comparing the null effect and the alternative hypothesis. So the first effect is the main effect for factor A, our first independent variable. So just IV1. It's basically asking us to, is there a difference just in this particular variable? It compares the marginal means of just the levels of factor A, and marginal means will hopefully make more sense as we move forward. The main effect for B is our second hypothesis. Again, we're comparing the marginal means for the levels of factor B, our second independent variable. So these two hypotheses are about just the factors by themselves. Does the independent variable, number one, have an effect on our outcome, regardless of what's happening with our second independent variable? The second main effect is, does our second independent variable, or factor B, have an effect on our outcome regardless of what's going on with factor A? And then finally, we have that third hypothesis. Is there an interaction between factor B and factor A? It examines the additional variance beyond the isolated effects of independent 1 and independent 2. It compares the group means to the marginal means. In other words, do we see that there's more going on than just the main effects? In other words, one factor depends on the level of the other factor. And again, we're going to go through some examples that will hopefully help illuminate this as we move forward. So when we're thinking about the two-factor ANOVA and the partitioning of variance, the first thing we're looking at is just the total variance, everything that's going on in that ANOVA. And then we're actually looking at between treatments and within treatments. So we're trying to partial that out. And then within the between treatments, we're partialing out factors A variance, factors B variance, and the interaction of factor A and B's variance. And again, if this was a more complex design, we'd be looking at even more. But we're still looking at the between treatment. In other words, is there an effect divided by the within treatments, which is usually where we're going to have our total variance and our error. In other words, is there more going on than just the variance that explains that there is something occurring either in factor A, factor B, or the interaction? And again, much like before, this is an omnibus test. We're going to get an omnibus test for factor A, an omnibus test for factor B, and an omnibus test for the interaction. If those are significant, that's simply saying that we can now look further. So for example, if I found there was a significant factor for A, there was not a significant factor for B, and there was not a significant factor for the interaction between A and B, the only one that I could continue on is factor A. I would then look to see basically a Tukey's test depending on the number of levels. If it's only 2 levels and it's significant, I don't need to do an additional test. I know there's a difference. I'm done. However, we'll assume there's 3 or more. We can have any combination, by the way, of significance here. We could have factor A and factor B be insignificant. There is no main effect of A, there is no main effect of B, but there is an interaction. It's significant. We would then get to look at the interactions and do additional testing. We might have a situation where either factor A or B is significant and we have an interaction. We could have a situation where factor A and factor B are both significant and there isn't an interaction. These are independent of each other, in other words. There is any possible combination because whether there's a main effect in A, whether there's a main effect in B, and whether there's an interaction, those are somewhat separate from each other. They're 3 different questions, and we're testing them separately in this omnibus test. So main effects versus interactions. The main effect for A is basically just looking at the effect from A divided by total error. When we're looking at the main effect of B, we're looking at the effect of just B divided by total error. When we're looking at the interaction, we're accounting for unexplained differences between the variations between all conditions, in this case a 2 by 2 design, which is 4, and the variations accounted for by factor 1 and factor 2. In other words, it's a little more complex. We're looking at the total effect minus the effect from A and minus the effect from B divided by error. In other words, is there anything left to explain after we look at the main effects? And we look at the main effects first. We give the error, the effect from A, and we look to see if that's significant. We look at the effect of B, and we look at that significant. And then we ask, is there additional effects that are occurring above and beyond these main effects? So degrees of freedom in a two-factor ANOVA, the notation presented and the BS and within subjects ANOVA, so the between subjects and within subjects ANOVA, have the same meaning here. K equals the number of groups or conditions. The degrees of freedom for each hypothesis test. For factor A, it's the number of conditions or the number of groups minus 1. For factor B, again, we're looking at the number of conditions minus 1. For the interaction, we're looking at those multiplied by each other. So if we had 2 and 2, so 2 minus 1 is 1, and then factor B, 2 minus 1 is 1, and then the interaction, 2 minus 1 is 1, multiplied by 2 minus 1 is 1, which is 1. So within error is always going to be basically n minus the number of conditions multiplied by themselves. So for example, in this case, we know there's 2 conditions. This is a 2 by 2 ANOVA. So n is minus 2 times 2, which is 4. So n minus 4. Total number of participants minus 4 is our degrees of freedom error. So we have 3 different degrees of freedom. We have a degrees of freedom for our main effect for A. We have a degrees of freedom for our main effect of B. We have our degrees of freedom for interaction. But then all of these have the same error degrees of freedom, which is n minus the 2 conditions multiplied by themselves. Now notice this would be different if we had more conditions. So for example, let's think about what if we had a 3 by 3 design. So 3 minus 1 is 2, so our degrees of freedom for factor A would be 2. Degrees of freedom for factor B would again be 3 minus 1, which would be 2. And the interaction now would be 2 times 2. It'd be 4. That's our degrees of freedom. And our n would be 3 times 3, 9. So n minus 9. So this also lets you know that as we get more complex, our degrees of freedom goes down. It becomes less likely that we can claim an omnibus test of differences, whether we're looking at main effects or interactions. So statistically speaking, again, we're simply looking at the sums of squares. In this case, the sums of squares just of factor A, or our first independent variable, divided by degrees of freedom, and then errors in the bottom. And then our main effect for B, again, is the sum of squares of that second variable, again, divided by the degrees of freedom, and we're looking for those effects. The interaction is actually accounting for any unexplained differences between the variance in all conditions, 4 in this case, and the variance accounted by factor 1 and factor 2. So basically, it's the sum of squares between minus the sums of squares A minus the sums of square B. And again, that's going to give us our sums of squares of the interaction. We're going to divide that by degrees of freedom. That's going to give us our MS squared for the interaction, and we're going to see if that's significant as well. So marginal means are the means of each level of one factor isolated across the levels of the other factor. A main effect test compares, in a two-factor ANOVA, the main effects, the marginal means of the level of factor A by the marginal means of factor B. So an interaction is when the mean difference between the treatment conditions are different than from what was predicted by the main effects. One factor depends on the level of the other factor. The trend for one level or factor is different from the trend of the other level or factor. Now, some of you this may make sense as far as just writing it down and thinking about it within the words, but we're also going to go through some visual examples. I want to make a note that visual examples do not represent necessarily whether or not it's significant. It's more talking about how to conceptualize this. So here we have an example of eyeballing main effects. So again, we have 2 independent variables. First is major, psychology majors versus anthropology majors. We also have a second factor, lowerclassmen versus upperclassmen. And we have the means of each group. So if we're looking at the first block, psychology majors that are lowerclassmen, we see a mean, which is their GPA of 2.5. If we look at psych majors and upperclassmen, we have a mean of 3.5. Likewise, if we look at lowerclassmen in anthropology, we have a mean of 1.5. And if we look at upperclassmen, we have a mean of 2.5. This is probably a good time for me to mention these are made up numbers. I'm not necessarily trying to say that if you're an anthropology major, your GPA is lower than psych majors. I really don't know. This is just to kind of give us something to look at and think about. So the marginal means mean that we're basically adding the 2 means together and dividing by 2. So 2.5 plus 1.5, again, we're going across the row of lowerclassmen. That equals 4. 4 divided by 2 is 2. The marginal mean is 2. If we're looking at upperclassmen, again, we're looking at that next row, we see that the psych majors are 3.5, the anthropology majors are 2.5. We add those together, 3.5 plus 2.5 is 6, divided by 2 is 3. Therefore, if we're looking at just class level, upperclassmen versus lowerclassmen, our marginal means are 2 and 3. In other words, upperclassmen have a 3-point GPA, lowerclassmen have a 2-point GPA, ignoring what major they're in. Likewise, if we look at the columns, we're doing the same thing. So psych majors 2.5 to 3.5, we add those together, it's 6 divided by 2, the marginal mean is 3. And anthropology majors 1.5 plus 2.5 is 4, divided by 2 is 2. So again, ignoring class level, lower or upper, just looking at the second factor, we actually see that there is the same effect. Again, psych majors have an overall GPA of 3, ignoring class level, and anthropology majors have an overall GPA of 2, ignoring class level. So again, we can say psych majors have a higher GPA than anthropology majors. Upperclassmen have a higher GPA than lowerclassmen. These are the main effects. Now, the question of interaction is there anything else left going on? And the way we do this is, again, if we look at factor A, there's a main effect. These are not the same. Now, again, is this statistically significant? I haven't answered that question. This is just visually kind of eyeballing main effects. So if I'm looking at the main effects for the rows, lowerclassmen versus upperclassmen, there is a difference. So I would say there's probably a main effect there. Likewise, if we looked at the columns, again, there is a difference. There is, looking at the marginal means, 3 is not the same as 2. There is the likelihood of a main effect there. For the interaction, what I'm looking for is the pattern going from box to box. So for example, when I look at lowerclassmen going from psych majors to anthropology majors, I find anthropology majors are 1 point lower on GPA. I find the exact same trend when I look at upperclassmen going from psych majors to anthropology majors. So it doesn't look like an interaction is occurring there. Likewise, if I go from lowerclassmen to upperclassmen, in both cases, I see a +1. So there is no trending difference between these boxes. In other words, the main effects are explaining everything. There really isn't anything else going on in this particular data set. There is no interaction. So again, just kind of walking through all of that, that's what we're looking at. Now let's take another look at a different example. So in this case, I've changed those means a little bit. So again, this is just eyeballing this. We're not looking at statistical significance. And again, these are made up numbers. In this case, lowerclassmen, the psych GPA is 2.0. The anthropology majors are 1.0. When we look at psych majors upperclassmen, 4.0 to 2.0. Now again, we're going to look at those marginal means, lower and upperclassmen, 1.5 to 3. So we can say that upperclassmen do, on average, perform better than lowerclassmen. So we have a main effect. And if we look at psych majors versus anthropology majors, again, psych majors have a GPA of 3, anthropology majors have a 1.5. We can say there's a main effect of majors. Psych majors score higher than anthropology majors. But let's look a little deeper at the actual trends that we're seeing. So again, we have that main effect just as we did before. We have that second main effect just as before. But now when we look at the trends, we find some differences. So when we go from psych majors at a lowerclassman from psych to anthropology, we see a drop of 1.0. So in other words, 2.0 to 1.0. But when we look at upperclassmen, we actually see a difference of 2. So it goes from 4.0 to 2.0. So there's a difference in those trends. Likewise, when we look at going from lower to upperclassmen in psych, we see an increase of +2 to their GPA, but only a +1 in anthropology majors. In this case, we would claim there is an interaction. Again, this is eyeballing. We don't know if it's significant, but that's how we're actually identifying a interaction when we're looking at these kind of data sets, is there's a difference in the trend above and beyond. Not only is there a difference between psych and anthropology majors, not only is there a difference between lower and upperclassmen, these differences change depending on your major. So for psych majors, we actually see them go up 2 whole points when they go from lower to upperclassmen. We only see it go up 1 point anthropology to from lowerclassmen to upperclassmen. So the differences get bigger as they advance from lower to upperclassmen in these 2 majors. There is an interaction. We'll talk about this and talk about some other ways to look at this data, But this is really, again, the 2x2 design is fairly simplistic. However, at the same time, there's a lot going on. We're looking at the main effects for the first independent variable. We're looking for the main effects for the second independent variable. And then we're looking for the simple main effects in that interaction to see if there's additional information going on.